Any questions? No? Let's look at our syllabus schedule. Tentative lecture schedule. September 17th, we talk about ranking, power generation cycle, and nucleation cycle. And then Friday, shortly is handling. And homework 5 is assigned for Friday. I'll give you some updates on homework. Why? You can see next Wednesday, our first exam starts next Wednesday. Yes, 1 week from today. Exciting. Oh yeah, very interesting homework recently. But it's time consuming, it's very time intensive. As you can see, you will be given 1 week take home exam due. So it starts from next Wednesday, you will be given 1 week to submit. Yes, there will be 7 questions. But how nice I am. I will show you 1 question, exam question next Monday. So the next Monday, what I show you is exactly that 1 question exam. You know how nice that is, huh? So what do you think? I will show you next Monday 1 exam question means you better finish the homework earlier before that Monday lecture time. So even though homework is already available, people can prep for, but Friday I'll give you more information about the homework. Just finish it during that weekend, and then next Monday when I show you 1 exam question, you can finish that 1 question. But official exam start from next Wednesday. Only 1 rule for that exam, take-home exam. You cannot discuss anyone. Only 1 rule. You cannot discuss anyone, each other, including me. You can ask me some question, general question, but not a technical question. You do all by yourself. That's the exam 1 is. Is it clear? Don't talk to anyone, don't discuss anything about Aspen, about this class. All do by yourself, as much as you can do, and just submit it. Submit same as like homework. Submit through the blackboard. Anyway, we'll talk about detail next Wednesday, but that's our scheduling. Let's talk about ranking, power generation cycle, and the refrigeration cycle. You have heard about Carnot cycle, yes? Carnot cycle? Yeah, Carnot cycle? Yes. What is the Carnot cycle?
There's no change in entropy in it. Is that what's? It's a refrigeration cycle, isn't it?
Refrigeration cycle.
It's the most efficient.
No energy loss. Okay.
Most efficient.
That's
Or
the most efficient.
no energy loss. Okay, good. What else?
It's the most efficient
Most efficient
heat cycle.
steam engine.
Yeah.
Kind of. Most efficient steam engine cycle. From this Carnot cycle, simply or industrial revolution started. For steam engine, you know, steam engine. For train transportation, we start using steam engine. We developed coal-fired power plant, natural gas-fired power plant, all based on Carnot cycle. So the Carnot is person's name, French engineer and physicist. Initially, he got that idea, so we call Carnot cycle. As you can see, his name is Sadi Carnot. In 1824, he proposed and published that idea. But 1830s and 1840s, the Scottish engineer and physicist is called William Rankine. He expanded the Carnot's idea to complete that power generation cycle. So we call it called Rankine cycle. So who should get more credit for this idea? From my opinion, Carnot should get more credit. Or else who invented first should get more credit. So from my opinion, Carnot should get more credit, but Rankine expanded and completed that theory. So what this theory means, to predict the performance of steam turbine system, in this case, to convert heat into mechanical work. Convert heat to generate electricity. Convert heat to run our steam engine used in real-world applications. Rankine cycle is used in steam power plant to generate electricity. Carnot cycle, Rankine cycle. Amazing topic. If you look at this Rankine cycle, in this case Rankine power generation cycle, we have one pump, boiler, turbine, condenser, pump, boiler, turbine, condenser. It's closed system. It's not open, it's closed system. As long as we input some water, in this case 10,000 kilograms per hour of water, this water will just continuously circulate in this closed system and generate electricity. Rankine cycle. Somebody says we don't lose anything. Yes. Somebody says it's very efficient power generation cycle. Yes. If you look at next slide, amazing. Exactly same concept and idea. And then engineers developed this idea for refrigeration cycle. So if you look at it, refrigeration cycle, we use compressor, condenser, valve, evaporator. It's also a closed system. In this case, we just replace water with some refrigerant, ammonia in this case, or propane gas. A propane gas used in forklift, propane gas. Nowadays, hydrocarbons, CO2, demethyl CFC, HCFC, those refrigerants. Only replace water is refrigerant, we can develop refrigeration cycle. Imagine this Rankine or Carnot cycle and refrigeration cycle. How much their idea contributed to our daily life. Think about it, it's our refrigerator, how can you survive nowadays? Yeah? Huh? So, the contribution to our human daily life, huge contribution. As I mentioned, from the Carnot cycle, Rankine cycle, simply the industrial revolution started, while bloom. But anyway, we will design, let's look at it, the Rankine power generation cycle first, using astronomy. So, I will use chemicals is metrically. I will ask some very interesting question on the way. So please concentrate. Please concentrate what we're talking about. First, the power generation cycle, we only use water. Water, if you go method assistant, recommend to use steam table. So I can choose IAT WS 95. International Association for Properties of Water and Steaming. That's most recent steam table. Okay. We have only one component, so don't worry about binary international parameters. We will have warning says binary parameters are missing. We only use one component, so it's okay. As you know, okay, we have one pump. And we have boiler and condenser, and then we have turbine. Turbine, pressure changers, turbine. Okay. Let me rotate this icon so that I can connect steam well. So let's try to connect steam in. Okay, let's name it. This one is pump. This one boiler. This one turbine. control turbine for what? To generate electricity. So I will connect to work the steam to generate electricity. So we generate electricity. Let's name it this steam cold water. This one high pressure steam, low pressure steam, and this one just water. Okay? Let's input our initial water flow. So you go here, 25 degrees Celsius, 1 bar, and then water mass flow is given. So I will put water 10,000 kilogram per hour. We are working on boiler. So if you look at the slide, boiler, temperature 460, pressure 40 bar. It's all given, so I think we'll put it in. I am working on condenser, 90 degrees Celsius, 1 bar. Let's go. We are working on pump. Discharge pressure is given, 40 bar. Efficiency is not given, just leave it. Aspect will take 100%. And whenever you are dealing with pressure changes, please check the pressure options. Repeat only. Yes, okay. Then we can go next. We are working on turbine. So turbine, I click turbine. Isentropic. Discharge pressure is given, 1 bar. Efficiency is not given, just leave it. Turbine pressure changes. So check valid cases. Turbine has vapor and then liquid. So I can use vapor, liquid. Okay. So our simulation is done. What we are looking at here, let's look at, can I look at it, temperature, pressure, vapor pressure. So we will pay attention here. So initial water was about 90 degrees Celsius, 1 bar, and the vapor pressure is 0 because water is liquid. We pumped, okay, to 40 bar, high pressure, and we produce steam, high pressure steam using boiler. At that time, the temperature is 460, 40 bar. We produced high pressure steam, so vapor pressure is equal to 1. We use this high pressure steam to generate electricity through turbine. So let's look at how much electricity is generated. So we can look at it. How much electricity? What do you see? Ryan, can you see?
Negative 16 kilowatts.
So what does negative means there? Leaving, in this case, leaving is not good word to express this one. Huh? Being used? I don't think so. Page was smiling.
I was just laughing.
Oh, Harrison. What is negative means in this case? Jackson, can you help me?
Is it the maximum?
Maximum? Oh, wake up this side, let's go this side.
Is it power generated?
Huh?
Power generated?
Power is generated. Power is generated. We are generating electricity. Negative sign in this case. Look at it. Look at power, kilowatt, electricity. Negative sign means power is generated. Right. If it's positive sign, what do you think? Power lost, not good expression. Forget about this side.
Required?
Weston.
It's the power required to.
Power required. Okay. Yes.
When you were doing the turbine, why did you do vapor and liquid? Wouldn't it just be vapor if it's diluted?
Okay. So, for example, look at it. If in this case we have high pressure steam, yes, And then high pressure steam, you increase the temperature and pressure to generate electricity always more efficient. So current, the normal power plant use very high temperature and pressure simply to improve efficiency. How much can I generate electricity? So you increase the temperature pressure, you produce high pressure steam. Nowadays current power plant they use supercritical high pressure steaming to generate electricity. Now this steam, high pressure steam flows through the turbine, generated electricity during that time. High pressure will condense to liquid. So in turbine there is called steam and then there is a liquid. Alright, if I choose here only vapor only, so initially it was vapor only, that's your question. And if you reset and run, you may get some warning. It says there is some liquid exists in turbine. Do you see? No warning? That's not so. No warning means no liquid is existing. That's fine, right? Good question. Usually, what happens? I think in this case we have very high temperature. Maybe it's not condensed at all to liquid. But in normal industry case, right? After you generate electricity, as I mentioned, that high pressure steam will condense to liquid. So if the liquid exists there, how do you deal with? Sometimes ASCII may send you some warning or anything. That's why I chose. But in this case, it looks like we produce high pressure steam. After turbine is low pressure steam, still temperature very high, vapor pressure is 1, so vapor only also fine. But same thing, I chose vapor liquid equilibrium also work fine, vapor only also work fine. Very good question. But now you understand what is going on here. Okay? So we use the high pressure steam, generated electricity. How much electricity is generated? It's about 1628 kilowatt. In US, average residential house, how much electricity do we use per month? A lot? A lot is not good answer. Guess at some number.
That much?
Huh?
That much?
That much, good guess. 1,000 kilowatt. We consume about 1,000 kilowatt. Average US residential house, about 1,000 kilowatt. You are living dormitory or apartment, maybe a little less, 600, 700 kilowatt. Some person I use a lot. For some, resident house, they use a lot. Do you know? Should I say this or not? But I think it's true, so I can tell. So US average house residential use is about 1,000 kilowatt hour per month. Do you know Elmore?
It was Clinton's vice president.
Huh?
It was Clinton's vice president.
Okay, he was vice president during the Clinton administration. He got Nobel Peace Prize. Why? He got Nobel Peace Prize. Why? Anybody? He was vice president of the US during Clinton administration, and then he got Nobel Peace Prize because of his activity, his actions against climate change. You know climate change, greenhouse gas emission, climate change, greenhouse gas emission. Greenhouse gas emission, what is the main contributor to greenhouse gas emission? Carbon dioxide. Simply from electricity generation, we try to use coal-fired power plant, generate electricity, emit a lot of carbon dioxide. Natural gas-fired power plant. As long as you use fossil fuel, yes, you burn fossil fuel, produce CO2, which is main contributor to greenhouse gas emission. Al Gore, his activities against climate change and greenhouse gas emissions. Yes, because of that, he got Nobel Peace Prize. How much electricity does he use per month? His house in Atlanta, he lived in Atlanta. $200 Anyone else?
10,000.
10,000. Anyone else? 300.
2,000.
Zero.
Come on, it's guessing, doesn't matter. Come on. No idea?
Zero. I'll look it up.
150 kilowatt hour. He has a big house in Atlanta.
3,000.
3,000.
4,000.
Let me give you. After he got Nobel Peace Prize, CNN reporters find out information statistically, and then they reported Al Gore got Nobel Peace Prize because of climate change, against climate change actions and activities. Well, CNN reporters find out he used 40,000 kilowatt per month. Per month.
Oh, his newest one's 231,000. They did another one. It's 231,000 kilowatt hours now. That's even more.
What a hypocrite. After that before, he disappeared. Can you see nowadays? Can you see him nowadays on any media? So after that, before it's CNN reported, and then he's not on media anymore. But ironically, he got Nobel Peace Prize. But anyway, what we are talking here? We are talking. We used 10,000 kilograms per hour of water. We can generate about 1,630 kilowatt of electricity. More than like one or two residential house electricity generation. Now, if you look at here, we used to pump. So let's look at how much energy is required to pump and boiler all those things. So after you simulation it over, you can check how much energy power is required to pump. As you can see, it's about 26 kilowatt power is required to pump 10,000 kilogram hour of water. Now we can check the boiler, okay, how much heat is required. So as you can see, heat is required in gigajoule per hour. About 30 gigajoule per hour of heat is required in that boiler. Boiler means we use steam or we burn natural gas and to boil the water to produce high pressure steam. Now check the condenser. As you can see, we can check in this case negative value for heat is extracted in this case negative value for condenser or heat. The heat is extracted from the condenser. It's about 24 gigajoule per hour heat is extracted in. Yes? You get some idea, right? You get some idea now what's going on? Yeah? Now, the question here. Look at the cycle. We pump water, yes. We boil that water, produce high pressure steam, generate electricity. We still have low pressure steam, which is steam. But we condense to water and pump, boil again, produce electricity, and condense water again. Pump, boil, produce electricity, and condense water again. My question here is, as a chemical engineer perspective, can we maybe remove this condenser? Yes. Can we circulate the steam continuously? As I said, steam produces electricity more better than anything else. my question is, can we just circulate steam so that we can eliminate this condenser process to condense water, pump, produce high pressure steam?
Are you just asking the low pressure steam can just go back to the boiler
Yes.
in real life or in theory? In real life or in theory?
In real life or theory, well, it's possible, isn't it? So we have high pressure steam. At the turbine, we got low pressure steam. Can we directly circulate to the boiler that low pressure steam to produce high pressure steam? That means we can eliminate the condenser. Maybe we can also eliminate pump. Maybe we can install compressor. As long as we can install something to circulate this high pressure steam, then it will be more efficient or profitable. They developed the 1820, 1830s. That's exactly the same idea. Why after 1830s, we maybe tried something different, but we are still using the same ranking cycle, exactly the same cycle. We didn't improve anything after that. We think about different approach, but we found out that was so much efficient than other approach. So, what I suggest here, if we try to do that, it's not that efficient, it's not that profitable either. Yes, that's why we are still using this cycle. But you can imagine what I'm asking here. Yes? Why? The question is why? Let's go quickly, come on. Anyone?
You need a driving force to keep it circulating.
Hmm?
You need a driving force to keep it circulating. You can't pump.
Yes. So you cannot pump gas,
Yeah.
right? That's why we condense water and pump, because you cannot pump gas in a vapor phase. Good point. What else? What else? Canon. I think Canon has a good idea with this.
I was
No
gonna say,
idea?
I was gonna say what Chase said, you can't pump the vapor.
Okay. There's another very critical point. Not only applicable for this system, applicable for a lot of other cases. Any idea?
Do
No.
you lose water or steam through the process?
No, we don't lose anything here. It's a closed system. Unless there's a break or leak, we don't lose anything. But the question is, we condense the water and pump, and then boil again. Condense the water and make the vapor. Condense water, make the vapor. We are keep changing still.
Is the pump suited for vapor?
Hmm?
You can use a compressor to a bit, right?
So maybe Steve's idea, maybe pumping is cheaper than circulating vapor. Eh? That's correct. Yeah, same thing, similar thing. I'm looking for another answer. Okay, I give you an idea, right? So as I said, this cycle is much more efficient and profitable and very effective, practical. The reason is, okay, we cannot pump vapor, but we can use compressor. But as I said, pump is less energy consumption, and then compressor uses more energy. Okay, that I will do. Okay. Another one is, if you look at this system, if we try to just circulate vapor, then this system requires a huge piping system. Why? Vapor density, think about it. Water density, 1,000 kilogram per cubic meter. Air density,
It would be really
1
loud.
huh?
It would be really loud.
Really what?
It would be really loud, like steam running through pipes.
Maybe really loud, okay. Possible, but we are talking about volume here in this case. Okay? So if you only circulate vapor phase or gas only, it requires a huge size of piping system. That's another reason we condense water using pump. So using pump is less costly. Also, it requires, by condensing to water, it requires less infrastructure. Okay? Very good idea. Where can we apply? I don't know if you are interested in. US right now we export a lot of liquefied natural gas, liquefied LNG, natural gas, liquefied natural gas. How do we export to Asian countries and European countries liquefied natural gas? How can we make the liquefied natural gas first?
High pressure.
Huh?
High pressure.
No. Good guess, no? Come on, let's go. Keep the time. Low temperature. Negative 162 degrees Celsius. At room temperature, you keep very low, room pressure, you keep very low temperature, you can liquefy. The natural gas is gas, no? But we make liquefied natural gas. Why? Why do we try to liquefy? We can store more, we can transport more. So if you look at that LNG shipping, the shipping huge ship, they can transport a lot of natural gas to European country, which almost the one country can use like 6 months for one shipping. So as long as you condense to liquid, it's much easier to handle, less costly, and then much more efficient and profitable. Very good idea, right? Now, only question is how can you keep that low temperature? Well, that's the question. But the France company has that patent to keep this natural gas at that low temperature. But anyway, so think about that one. Let's continue. We will design very similar cycle for refrigeration. So I am going to use the same flow sheet. So let's try to design and simulate refrigeration cycle. So in this case, we have compressor, okay, and we have condenser, evaporator, and we have a throttling valve. So I will choose this one. So let's rotate icon. Let's connect material flow. In this case, compressor. Condenser. Valve and evaporator. We use ammonia, so I will name it compressed ammonia, condensed ammonia, throttle ammonia. We use ammonia to be able to define, specify a component, ammonia. So let's go back to property window. I will put ammonia. And we don't know what property method to use. So let's go for now. Run the simulation. Now, if I run this simulation, what do you expect? We didn't put any information yet, so let's go compressor. Okay, isentropic, discharge 6 bar. Let's go continue. I am working on condenser. This information is all given, so please, pressure drop is given, and the vapor pressure is given. So while the vapor pressure is equal to 0, pressure drop is equal to 0. Let's continue. I am working on evaporator. Pressure is given 1 bar and vapor pressure is given. So I will choose vapor pressure is 1. And let's continue. Throttle is our pressure 3 bar. And what is it? Compressor. I prefer choose valid phase, vapor liquid. We can check. If I run this simulation, what do you expect to see the results? Any idea? Hi, should I run the simulation or not?
Wouldn't hurt.
You missed the Monday class. We cannot run the simulation this way. Oh,
You have to like section it out into.
wonderfully. Why? Power generation cycle we used water, liquid, yes. So we used the steam table property method. Now in this case we are using ammonia, gas, okay. So let's check. If you go property method assistant, we are working on using ammonia. So if you go, maybe we can choose refrigerant. Ammonia is refrigerant. Now the method assistant recommend to use refrigerant property method. Huh? Yes, you cannot use the same property method for 2 different simulations on one main flow sheet. So as Weston said, we can sectionize. Yes. So let's try to sectionize the first one. Select that flow sheet and right click on any unit block, and you can change the section and define new section. I define S-1. Select your second flow sheet, right click on any unit block, and for change section, create new section S2. So we have 2 different sections. We can specify 2 different property methods. For this one, maybe steam table. For this one, equation of state-based property method. But how do we do it? If you go property window, as I said, for specification under method folder, and then flow sheet section tab, you can choose S1, steam table, S2, method assistant recommend, refrigerant property, so RDF property method. Okay? And this long simulation here, let me just reset just in case. To reinitiate calculation. Now we can learn 2 different process in one main flow sheet. We are not using global anymore, so for right click and you can delete global. So we got no warning, no error. Okay. Now what we are interested in, if you look at here, okay, this is refrigeration cycle. So please look at the temperature profile in this case. Okay. Right now, after the throttle valve, the temperature is 9 degrees Celsius. And after evaporator, the temperature is negative 34 degrees Celsius. Refrigeration cycle. By using 1,000 kilogram per hour of ammonia in this case, very similar to power generation cycle, we could produce this refrigeration cycle. Amazing thing here, if you change it in bulb, so if you look at your home refrigerator, how do we control the temperature? If you just change that pressure, let's say initially 3 bar, if you change to 5 bar, we can easily control this refrigerator temperature. What do you see now? 4 degrees Celsius. Yes, it's about 39 degrees Fahrenheit. Your refrigerator temperature. Also, you can easily change that pressure, and you can control this output temperature for refrigeration cycle. So initially was negative 34, now it's negative 19. Your freezer temperature. Yes. Now, wake up everyone. The question here. Evaporator does not require any power, any electricity. Evaporator is just a device. If you look at your refrigerator, backside of your refrigerator, have you ever seen how does evaporator look like?
It's a copper coil.
Copper coil. Wonderful. Jace, can you explain us why we use like a coil?
It functions as a heat exchanger with the air in your house. It uses the heat from outside.
Heat, okay. So good point, but that's the one reason. What Jace says, evaporator looks like this coiling. Have you seen this kind of coil? The backside of the refrigerator. So these are tubing. So if I draw example is tubing. Tube coil. Who invented this evaporator? Become multi-millionaire. Why? Jason says to improve that some heat transfer. There's another reason. Yes.
Using like centrifugal force to.
Centrifugal force. Evaporator. What is evaporator?
Makes it warmer.
Makes it warmer.
Service area. Service area.
Surface area or volume to increase volume. If you design this just a straight piping system, compared to this straight piping system, coil makes a large volume. Yes. Evaporator. What's the purpose of evaporator? Simply, we want to convert liquid phase to vapor phase. That's evaporator. As I mentioned, convert liquid to vapor or convert vapor to liquid. We are more focusing on volume control. Evaporator. Simply because we convert liquid to vapor, it requires more volume. Coil design, you can keep a lot of gas than just straight tubes designing. Who invented this one? I say very simple idea, just make more volume. Apply to every refrigerator. Very simple idea. As long as you apply pattern, you become multi-millionaire. Yes? That's what the evaporator is. So evaporator simply is a device, nothing. It doesn't require any power. Okay? Only change the volume larger so that we can make, for example, in this case, liquid. We convert liquid to vapor. But anyway, refrigeration cycle is so simple. By just controlling the pressure, we can control the temperature. Refrigeration cycle. Yes. Now, problem solving for refrigeration cycle. In this case, use SRK method and use propane as working fluid. So please try to solve these 4 questions for your practice. Determine the vapor pressure at which propane can be condensed at 45 degrees Celsius. Determine the vapor pressure to which propane can be evaporated at negative 50 degrees Celsius. Use result 1 and 2. Determine the amount of propane necessary to extract 1 gigajoule power of heat in the evaporator. You got idea of those questions in? Yes? Let's try to solve the first question. What it says, determine the vapor pressure. What we use? In this case, we use propane. So let's try to define propane. Okay, and it says to use SRK method, so we can use SRK method. Steam MDS. Now the first question was determine the vapor pressure at which propane can be condensed at 45 degrees Celsius. What does that mean? You can use this fuel analysis. And then it's called property. Vapor pressure. So if you hover your mouse, on PL, vapor pressure for pure component. Okay. Unit, maybe we can choose bar. Determine the vapor pressure of propane at 45 degrees Celsius, which can be condensed at that temperature. So I choose 45 degrees Celsius. We are working on propane. We use SRK method, run the analysis. Then check. We get 15.5011 bar. At that temperature, 45 degrees Celsius, at this pressure, propane can be condensed. Means propane change from vapor phase to liquid phase. We are going to use this information for refrigeration cycle design later. Now, second question is determine the vapor pressure to which propane can be evaporated. So, just change the temperature negative 50 this time. Okay. Same thing, run the analysis. And look at the pressure, 0.6924. At that temperature, at this pressure, propane evaporating. We are going to use this information for refrigeration cycle. Okay. So in this case, it's all propane. What does that mean? Condenser. Okay. We can use that information for condenser design. It says at 45 degrees Celsius, at this pressure, 15.5011 bar, at this pressure, the propane gas can be condensed. Yes? Another information, at evaporator, temperature, pressure, temperature negative 50 degrees Celsius, and pressure was 0.6924. At this pressure, the propane gas can evaporate. Yes. Can we reset? In May, hopefully it works. Okay. Fine. It's okay. Don't worry. Must be pressure here. Maybe pay for me. But anyway, so what this question is looking for, how much heat is extracted in this evaporator. So let's try to look at evaporator. Oh my goodness, did not work. The reason I didn't change the input stream. Okay, we are using propane here. Let's say initial gas was 3,000 kilograms per hour. What? Oh my goodness. Always going all the time. I'm sorry. But please be patient. So what's the question here? How much heat is extracted from evaporator? So let's try to look at evaporator. You can see by using 3,000 km per hour of propane gas. Okay. How much heat evaporated is about 0.5 to 7. We are looking for this one should be 1 gigajoule per hour. You can use maybe design spec to find out how much propane is necessary to extract 1 gigajoule per hour. Any questions? No? Let me make sure. Jacob, Nadia.